In the previous video, I explained why memory blocks of variables that store different data types are of various sizes in terms of number of bytes, and use different formats to store their values. I mentioned that there was a type of variable called a pointer, but I did not elaborate on that. In this video, I'll go into detail about what the pointer data type is, and also look at how different computer architectures store multi-byte blocks of data. In the previous video, I showed how positive and negative integers and fractional numbers, as well as individual alphanumerical characters, can be represented in binary using different data types for each. There is another type of number that is very useful to C programmers, numbers that represent memory location addresses. Because these numbers represent addresses, they can be used to direct or point a running program to a particular location in memory for the purpose of reading or writing the data stored there. For this reason, variables that store addresses are called pointers. In one sense, pointers are just like normal unsigned integers, because addresses are unsigned integer numbers. They start at 0 and go up in steps of 1 for each byte's worth of addressable memory in the computer. So why do we need a special data type for pointers? Why not just use an unsigned int? Well, there are three reasons why we need a separate data type to store addresses. Firstly, the size of this data type in terms of number of bytes needed to store a memory address number needs to be large enough to hold all the possible memory addresses a particular processor can handle. The size of an unsigned int may not be sufficient for this in some systems, but in other systems it may be too big and wasteful. Compilers compile code for certain processor architectures, so the size of a pointer will be implementation dependent. Having a separate data type for a pointer means the programmer doesn't have to guess or work out what type of integer to use, or change that data type in all their source code whenever they want to compile the same program for a different system, because the compiler will automatically use the correct size data type at compile time, according to what processor architecture it's compiling for. The second reason for a separate pointer data type is that, unlike standard integer data type variables, which only have one value associated with them, the value stored in their own memory block, pointers have two values associated with them. The first, which we can call the direct value, is the value stored in their own memory block, which is the integer representing a memory address location. The second, or indirect value, is the value stored at the memory location which that address number points to. Because of this dual value aspect of pointers, C has special syntax symbols that only apply to variables of pointer data type. These symbols allow you to access the indirect value of a pointer, that is, the value which the pointer points to, and the act of accessing this indirect value is called dereferencing the pointer. The syntax for dereferencing a pointer involves the use of the asterisk and arrow operators. I'll discuss arrow dereferencing in a later tutorial. The asterisk, when used with a pointer variable in this way, is called the dereferencing operator, or the indirection operator, for the reasons I described, and you use it as follows. Let's declare an int variable called myIntVal, and initialize it to have a value of 10, like this. To make things easier to read from now on, I'll not show the stored data in a memory location in binary, because this can get difficult to read when we do more complex examples. Instead, I'll use the equivalent decimal notation, so this example will look like this. Now let's declare a pointer to an int called iPointer. In C, we declare pointers using the data type they point to and an asterisk like this. Note that you need the asterisk at the time of declaration, that is, the time of first creation of a pointer variable, to show the compiler that this is a pointer variable as opposed to an ordinary int variable. We don't use the asterisk whenever we want to read or write or otherwise change the direct value stored in the pointer. We only use the asterisk again if we want to dereference the pointer, that is, to read or change the indirect value, the value it points to. The value currently stored in iPointer at the time of its creation will be some arbitrary bit pattern dictated by whatever happens to be in the block of memory assigned to that variable when it is created. This is true for any kind of variable when you first declare it, not just pointers. So for any variable, you shouldn't use the value it contains when first created without initializing that value to some meaningful content first, a process called initializing the variable. And you saw an example of initialization in what we did for myIntVal earlier. So let's initialize the value of iPointer to the address of the variable myIntval using the address operator, the ampersand, as shown. This copies the value of the address of myIntval into iPointer, not the value stored in myIntval, which in this example is 10. So, if we were to read the direct value of iPointer at this stage, we would get the result 653865, because that's the address of the variable myIntval. But if we were to read the indirect value of iPointer by using the dereferencing or indirection operator, we would get the value 10, because that's the value stored in the memory location pointed to by the address stored in iPointer. Now, this is of course the same result we would get if we just read the value of myIntval. So, in a way, putting the asterisk in front of a pointer variable is like changing that pointer variable into the kind of variable it points to. Using *iPointer has the same effect as using myIntval in this example. That's why when you create pointer variables, you declare them using one of the pre-existing data types but with an asterisk, because in this declaration example, *iPointer, when used together, behave like a standard int variable. You can even declare standard ints and pointers to ints in the same line, using a comma as a separator. So I could have written the declarations for both variables in our example code in one line, like this. This is not specific to the int data type. The same rules apply whatever data type we use. The third reason why we need a separate data type for pointer variables is that arithmetic works differently with the integer address values stored in pointers compared to the standard integer data types. So the compiler needs to know it's dealing with a pointer so it can implement this pointer arithmetic. So what is this special arithmetic? If you take an ordinary integer and increment it by 1, the value of that integer goes up by 1, as you would expect. In C source code, we can write this increment by 1 operation like this. So if myIntval was 10, after this operation it would have a value of 11. Other ways to write this in C are as shown. All these three do the same thing. However, the ++ notation only does incrementation by 1, but the other forms can increment by any value, as shown. You can use a similar set of expressions for subtraction, as shown. So that's ordinary arithmetic, all very familiar and obvious. Now, consider the pointer variable iPointer, whose integer value is the address of myIntval, so the current direct value of iPointer is 653865. What would be the result of incrementing iPointer by 1, like this? You might think it should be 653866, right? Well, no, that would be wrong. This is because iPointer is a pointer to an int, and because the value stored in iPointer is the address of an int, this address can only change in steps of n bytes, where n is the size of the int data type. For the sake of this example, let's say an int is 4 bytes long. So, if we were to translate these C source code expressions into English, each of them would mean increment the address value stored in iPointer to point to the next integer-sized block along the memory bank. So the address value in iPointer will be incremented by one lot of 4 bytes, so it points to the next int-sized block of memory. So the actual result of this increment by 1 procedure is 653869. That is 4 units greater than its starting point, where each unit is the address of 1 byte. Likewise, if we start from iPointer equals 653865 and increment by 3 like this, the result would not be 653868, but rather it would progress 3 lots of 4 to point to the address 653877. Similar step-sized jumps would occur going the other way with decrements, with each step being 4 bytes long in this example. Now, in this example, we only incremented in steps of 4 because iPointer is a pointer to an int, and for the sake of our example, we agreed that an int is 4 bytes long. If the pointer variable was a pointer to some other data type that was 8 bytes long, like a long int or a double, then it would be incremented or decremented in steps of 8. There are further rules of pointer arithmetic I will not cover here, but the general principle is that pointer arithmetic is scaled by the size of the data type the pointer points to. From this, it should be clear that, to do correct pointer arithmetic, the compiler needs to know not only that a variable is a pointer, but also what data type that pointer points to. For this reason, the way you declare any pointer variable in C is by reference to the data type you want it to be a pointer to, using the asterisk method as shown in these examples. So, the data type used when declaring pointers is the data type of the object the pointer is pointing to, not the data type of the pointer variable itself. So what is the size of the data type for a pointer variable itself? All the pointer variables shown here, regardless of the data type of the thing they are pointing to, store a single type of data as their direct value, that is, an unsigned integer that represents a memory location address number. So how many bytes does it take to store such an address number? The answer to that question is implementation defined. The compiler will decide, based on the CPU it is compiling the machine code to be run on, how many bytes are needed to be able to store any possible address value that that particular processor type can handle, and that will be the number of bytes allocated to the pointer variable. In practice, this usually equates to the size of a machine word, so it is 4 bytes for 32-bit processors and 8 bytes for 64-bit processors. So, although the arithmetic of incrementing and decrementing pointers depends on the size of the data type they point to, the actual size of the pointer variable itself is fixed for any given compiler-processor combination. It is possible, therefore, to define a kind of generic pointer variable that can contain an address of any memory location, regardless of what type of data may be stored at that location. This generic pointer is called the pointer to void, or void pointer, and you declare it like this. Doing this creates a pointer variable, so the compiler knows that the value it contains directly will be an address that needs to be handled according to pointer arithmetic for some data type that we haven't yet defined, and that this pointer can be dereferenced to provide a secondary value which will be interpreted according to that as yet undefined data type. However, in order for the compiler to actually do those things correctly, it needs to know what this undefined data type is. So, you will be forbidden from using those special properties of this pointer until you make that data type information available to the compiler. You supply that data type information using a C process called casting. Casting can be applied to any type of variable or function, not just to void pointers. It is a method that allows you to tell the compiler to temporarily treat a variable that is of one data type as if it were a different data type for the purpose of doing some specific process. Casting is done by putting the desired destination data type in brackets in front of the name of the variable or function you want to cast, as shown in this example source code that uses ordinary non-pointer variables. In this code, the value of my int and my float are both treated by the compiler as if they were doubles, but only on that one occasion where you supply the cast. Now, the natural data type of our pointer to void is a pointer, that is its data type. So, assigning address values to it does not require casting, because simple assignment of values is the same kind of process that it shares with all variables. You're not using its special pointer properties here. So we can do this assignment directly without a cast, as shown. But we can't do pointer arithmetic or dereferencing with a void pointer unless we tell the compiler the data type of the thing it points to. This means that if we try to increment the void pointer without a cast, as shown, the compiler will give us an error and refuse to compile. But if we use a cast like this, all is well, because we've told the compiler to treat pointer on this one occasion as if it were a pointer to a double. Note that we've cast it as a double star because it is a pointer. If we omitted the star like this, it would be an error, because this means we're trying to cast a variable that is of the pointer data type into a non-pointer data type that is not even an integer. In C, some examples of casting between pointers and non-pointer integers may be allowed, but may also result in errors. This is an advanced topic, and I will not go into it further here. You can, however, and must, cast the dereferenced value of a void pointer to a type that is legal for the dereferenced value. In this case, the dereferenced value is a non-pointer data type, a double, so you can cast the dereferenced value into any other non-pointer data type, for example, into a float, like this. But what if the variable pointed to by a pointer is another pointer? Because pointer variables are just variables, they are blocks of memory that have their own address, just like any other variable. If you want a variable to store the address of a pointer, then you simply declare this with the data type of a pointer to a pointer, using 2 asterisks like this. And you can keep on going with a pointer to a pointer to a pointer, like this. And you can continue to as many levels as your compiler will allow. You dereference such pointer to pointers using the number of asterisks that correspond to the level of dereferencing you want. For example, you can set myPointer to an int to store the address of iPointer like this. And you can then dereference once to get the value stored in iPointer and twice to get the value stored in the integer variable that iPointer points to, like this. Likewise, if you had a variable that is a pointer to a pointer to a pointer, you can dereference up to 3 times, and so on. Hopefully by now you can see that pointers are very easy to understand, but that misuse or lack of discipline when using pointers can result in very confusing programs. However, the appropriate use of pointers is sometimes the only way to get a particular thing done, or done most efficiently. So far in this course, I have been discussing only single variables of various data types. C also allows you to declare combinations of single variables that you can use and manipulate as a group. Some of these groups are called structures and unions, and I'll leave discussing those for another tutorial. The group of variables I'm introducing here are called arrays. You can declare a one-dimensional array of unsigned cars like this. In this example, myString is the name given to a block of memory that contains 10 unsigned car-sized memory locations. Because an unsigned car is just 1 byte, this means 10 bytes in this example. Just as with any variable, myString is the convenient name I chose which refers to the address of the first byte in this memory block. However, unlike an ordinary variable, C allows you to use the name of an array variable as if it were a pointer, albeit with an important restriction which I'll discuss later. This means you can access the contents of a particular element in the array in 2 ways. You can either use square brackets and a number indicating which element in the array whose value you want to access, or you can dereference the array name with an asterisk and use pointer arithmetic to point to that element. Note that in C, the number of an element in an array always begins at 0, not 1. So, the 2 C expressions shown both access the same value, that is, the value of the 4th element of the array. Note also that this dereferencing syntax with square brackets works for ordinary pointers too, not just array names. This also indicates another point of syntax for arrays in C, namely, when you use the name of an array variable without using square brackets in front of it, that is equivalent to using the name as a pointer to the first element in the array. Therefore, the 2 expressions shown here are equivalent. With these things in mind, let's consider another example. If I had a pointer to an integer called iPointer, and I set it to point to the start of an array of ints in memory, I could access the value of the 7th int from the start of the block by either of the 2 statements shown in this C source code example. We've seen that individual variables can be initialized at the time of declaration with an equals sign and a value. Arrays can also be initialized at declaration with an equals sign and a set of values separated by commas between braces, as shown. If you initialize an array like this, then you don't need to specify the number of elements in the array. Just use empty square brackets and the compiler will allocate the correct amount of memory for you, as shown. A special case of initialization is allowed for arrays of cars, where you may initialize them with a string of characters in quotation marks, called a string constant, as shown. In internal memory representation, a string constant always includes a termination character of absolute value 0, called the null character. This allows programs to know when the end of a character string is reached. When writing the null character in source code, you use a \0 like this. The backslash differentiates this from the printable character 0, which actually has a value of 48, not 0, using the ASCII code set. However, the null character is not shown in string constants in source code. This means the array shown in the example will actually be 6 characters long, not 5. Finally, note that arrays may be multidimensional, but you can read up on that in standard texts if you want to learn more. We've seen that the name of an array, when used on its own without the square brackets, behaves like a pointer. However, there is an important difference between this and an actual pointer. The difference is that array names used like pointers are not variables, but strict constants. whereas true pointers are variables. This means the address value stored in an array name cannot be altered, but the address values stored in a pointer can. For example, in this source code I have set up the pointer variable iPointer to hold the same address value as the array name intArray. The value stored in iPointer may be changed by incrementation and assignment operations, but the value stored in intArray cannot undergo these alterations. If you try to do something like this, or this, the program will not compile, and the compiler should throw up an error to explain why. With any multi-byte data type, like shorts, ints, floats, and doubles, etc., the computer has a choice of how to store the multiple bytes that make them up. Let's take this 4-byte int data type value as an example. The computer will keep these 4 bytes together in sequential memory addresses. However, some computer systems will store the byte that has the highest bit values, that is the big end of the value, in the first or lowest value address location, sequentially followed by the lower value bytes until we get to the lowest value byte called the little end of the value, which is placed in the address with the highest address value, as shown. This order of storing the bytes is called a big-endian byte order, because the big end comes first. Other computer systems will store the bytes the other way round, with the little end byte in the first memory address followed by successively higher value bytes. This arrangement is called little-endian. Each computer system is internally consistent with how it does this, so the only time it becomes significant to us is when we're exchanging data between computer systems of different endianness. This exchange of data between systems can occur in 2 main ways. One is via computer networking, and network protocols contain inbuilt systems to detect endianness and compensate for it. The other is when we copy files manually from one system to another, bypassing direct network transfer of the individual bytes, such as downloading a file in a specific format or using removable media to take files from one machine to another. Imagine this integer, saved in big-endian format by one computer in a file, and we take this file to another computer that uses a little-endian byte order. When we load this data into memory, it will load in the opposite order to the original. This means that in the original system, the integer would have one value, but when we query the value of the integer read from the file on the little-endian computer, it will report a different value, as shown. To address this problem, we can perform a task known as byte-swapping in our program to deliberately swap the order of the bytes from any multi-byte data type so that it gets read with the intended value when moving data between little-endian and big-endian systems. Some standard file formats include protocols to take care of endianness for us, so this byte-swapping procedure only need be done by us if we write programs that read and write data in raw binary form without using the protocols provided by special file formats. In summary, a pointer is a variable that stores an unsigned integer that represents a memory location address. The direct value of a pointer is this stored address. The indirect value is the value stored at the memory location referred to by that address. Pointer arithmetic is scaled by the number of bytes associated with the data type of their indirect value. Arrays are blocks of one or more variables of the same data type that can be addressed using the array name as if it were a pointer. Multi-byte values need to be byte-swapped when moved between big-endian and little-endian systems. If you like this video, please hit the thumbs up like button and view some of the other videos on my channel. If you'd like to support the project, you can do that by subscribing to this channel and telling others about it. If you'd like to help me continue this work, take a look at my Patreon page, where you'll find additional content and early bird access to future videos. Thanks for watching.